Right, so we have a modeling question here. We have the trajectory of a rugby ball, and then on the y-axis is the height of the ball, and then on the x-axis is the distance it's traveled horizontally from where it was kicked. We're told the ball travels in a vertical plane, which basically means that the motion of the ball is contained within a vertical two-dimensional surface. So basically it doesn't veer left or right, it doesn't curl or spin or anything. That's all that means. And we're told it reaches a max height at 12, so this point over here, if it reaches a maximum height of 12, then that means that that coordinate would be something comma 12. We don't know what the x-coordinate is right now, but the y-coordinate is 12. We also know that it hits the ground 40 meters from where it's kicked, so this coordinate here is 40, 0, and then obviously the origin is 0, 0, and because of the symmetry of a quadratic, that would therefore mean that the x-coordinate of this turning point would be halfway in between these 2 points, so it would be 20. And then we want to get a equation that links h with x. So basically find an equation for this quadratic. There's a few ways you can do it. The easiest two ways are to use the completed square form of a quadratic or to use the factorized form of a quadratic. The long way is to consider the full equation, or like the generic equation of a quadratic, and then put these three coordinates into that to then work out what a, b, and c are and solve simultaneous equations. You can do it that way, that's fine, it's just a lot longer. So I'd recommend the factorizing way of doing it. So what I mean by that is, because we know the two roots of 0, 0, or rather of 0 and 40, those are the two roots, then we know that our quadratic will have this form. So it'll be a times x multiplied by x minus 40. So this is the same thing as a times x minus 0, x minus 40. These are the two roots that we have, and that's the same thing as what we have over here. The a is there because there are many quadratics that go through 0 and 40. So the a enables us to basically flip between all of these different quadratics. Depending on what a is, that will give us the equation of one of these quadratics that goes through 0, 40. So if a is positive, the quadratic looks like this. If a is negative, the quadratic looks like this. And then the bigger a is, the steeper the quadratic, or the sharper that turn is at the top. So we need to work out what a is. That's our next goal. Work out what a is. We can do that by using the information that we have yet to use from our graph, which is this point over here. We've used the two roots of 0 and 40. That's where we got these two terms here from. Now we need to use this point over here to work out what a is. So 12, that's the y-coordinate, is equal to a times 20, so I'll write that as 20a, times 20 minus 40, which is minus 20. These two times together are minus 400. So this becomes a is equal to minus 12 over 400, just rearranging it, which is minus 3 over 100. Now we have a, now we have our equation for our quadratic. So it's this. Just putting that a back into the expression that we have up here. That is our answer for part A. And then for part B, the ball passes over the horizontal bar of a set of rugby posts. So you can imagine rugby posts look like this. The ball then flies over that. We're told that the rugby posts, the bar of the rugby posts, is 3 meters above the ground. Okay, so basically the height of this is 3 meters. And then we want to use our equation. So that equation is what we worked out over here, or rather this here. We want to use that equation to find the greatest horizontal distance of the bar from O. Okay, so we can consider the position of this bar to change. We want to find the furthest away that this bar can be from the origin such that the rugby ball passes over it. And you can imagine that that would be all the way over here. So this is 3 meters. That's the furthest towards the right the rugby post can be, such that the rugby ball passes just over it. We want to work out that x-coordinate over there. That will be the greatest horizontal distance of the bar from O. So then to do that, we know that this point here will have coordinate of some unknown x value and a y coordinate of 3. We can put that into this equation over here. So that then becomes y coordinate is 3. 3 is equal to minus 3 over 100 times x times x minus 40. So I'll cancel out the 3's from both sides and then bring this 100 to the left. So it then becomes 100 is equal to minus x minus 40. Again, I've just cancelled out the 3's. And expand the right-hand side. This is minus x squared plus 40x, and then I'll bring everything to the left-hand side. So it becomes x squared minus 40x minus or plus 100 is 0. That doesn't factorize nicely, but we can put it in the quadratic solver, and that gives us x is equal to 20 plus or minus 10 root 3. And as decimals, those two are 37.3 and 2.68. So then we want the greatest distance, the greatest horizontal distance of the bar from O. So therefore we pick the bigger one, the 37.3. The 2.68, what that actually represents in the diagram is when the bar is over here, on the left-hand side. The path of the ball is such that the height of it is at 3 meters for that horizontal distance of 2.68. But that's the closest distance that the post can be to the place where it's kicked. So the furthest distance is obviously going to be this one over here. That bigger distance is 37.3. That is our answer to part B. And then for part C, given limitation of the model, well, we haven't considered the dimensions of the rugby ball. That's all we can say for part C. We haven't taken into consideration the dimensions of the rugby ball.